Hi, thanks for joining me. It has been a while since I last uploaded. Apologies for that. I was at university and it was difficult to keep up to date with my uni work and make videos at the same time, but I'm now back home for the Christmas break, so I should be able to make a few more videos for you. Anyway, this is a number theory problem we've got today, and yeah, let's just get stuck into it. We have tau of n, which is known as the divisor function or the factor function, and it's simply the number of factors of a function n. So it's the cardinality of this set here, the set of positive integers d such that d divides n. Okay, so the number of factors of n. Anyway, we want to know, does there exist some positive constant c, so c is a fixed constant independent of n, such that tau of n is less than or equal to log of n raised to the power of c for all positive integers which are at least 2. So we want to know, does there exist some fixed positive constant c? Again, it's independent of n, such that the number of for any positive integer n, the number of factors of n is less than or equal to log of n raised to the power of c. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the short answer to this problem is no. So that means that there's no constant c bigger than 0, such that tau of n is always less than or equal to log n to the power of c for any positive integer n at least 2. So in other words, if you give me some positive constant c, then there exists some positive integer n which is at least 2, such that tau of n is strictly bigger than log of n raised to the power of c. Okay, but of course I can say that, but we want to prove it, and that's what we're going to be doing in this video, is proving that there doesn't exist a constant c. And what I've done first is I've written up a little fact here, and that is if n is written in this form here, so p1 to the e1 times p2 to the e2 times so on all the way up to pk to the ek, so each of these pi's here are distinct primes, so I've written n in its prime decomposition form, and each of these ei's here are non-negative integers, then tau of n, the number of divisors of n, is simply e1 plus 1 times e2 plus 1 times so on all the way up to ek plus 1. Okay, so this is a fact. I'm not going to prove it in this video. In fact, I've made a YouTube short, so a video which is under a minute long, in which I prove this result, so I'll leave a link to that in the description below if you've not seen that result before. Anyway, we're going to be using this to prove that this guy here is false. Now, one way we can prove that this thing here is false, in other words, prove that there's no constant c that exists, is to prove it by contradiction. So suppose, for contradiction, some constant c exists. So we're going to do exactly that. So suppose there exists c bigger than 0, such that tau of n is less than or equal to log n, oopsie daisy, raised to the power of c, and this is for all n positive integers at least 2. Now what we want to do is essentially find some contradiction, and I guess the most obvious way we can try and do that is to find an n that doesn't work. So find some positive integer n, such that when we plug it into this guy here, we're going to get that the left hand side is actually bigger than the right hand side. Now, using perhaps this fact here as a little hint, an intuitive guess would be try n of the form p1 times p2 times so on all the way up to pk. So simply the product of the first k primes. So let's plug that in. So then our left hand side is simply tau of p1 times p2 times all the way up to pk. But then using our little formula here, or using our little fact, sorry, here, with each of these ei's being equal to 1, we see that the left hand side is simply 2 to the power of k. Because each of these ei's will be 1, so that means each guy in the brackets here will be 1 plus 1, so 2. And we've got k brackets, so it's going to be 2 multiplied by itself k times, so 2 to the k. So the left hand side is 2 to the k. And our right hand side now is simply log of n raised to the power of c. But log of n is simply log of p1 times p2 times all the way up to pk. So this guy here is log p1 times all the way up to pk, and then that's raised to the power of c. But of course then we can use our log rules to write this guy here, the right hand side, sorry, as log of p1 plus log of p2 and so on all the way up to log of pk, and that's all raised to the c. And remember, we want to arrive at a contradiction, and what it is now is 2 to the k is less than or equal to the sum of a bunch of logs of primes and then raised to the power of c. So perhaps we can take the cth roots on both sides, and that's not going to change anything. So 2 to the k over c is simply going to be less than or equal to this guy here. And now it's not particularly clear what our next step is. Perhaps what we can do is bound all of these things. because we know log p1 is going to be less than or equal to log pk, log p2 is going to be less than or equal to log pk, and so on. So all in all, this is going to be less than or equal to k log pk. So we have 2 to the k over c is less than or equal to k times log pk. And remember that k is arbitrary. We can choose k to be as big as we want because there are infinitely many primes, so we can take n to be as big as we want. However, if we have kind of look at this, we have on the left hand side something growing exponentially, and on the right hand side we have something growing kind of linearly, k times this guy here. So it might feel as if we've actually kind of reached a contradiction already by taking k arbitrarily large, because this left hand side here is exponential and this right hand side is k, so linear, multiplied by something. But what's annoying here is this something here is dependent on k. So even though it's log and you might think, oh, it's growing really slowly, pk, remember, is growing a lot bigger than k. Okay, so without using things like the prime number theorem, it's not particularly clear how we can bound log of pk. So unless we want to use the prime number theorem, and ideally we don't because that's somewhat advanced, we can't kind of make a conclusion just yet. So perhaps the n we chose wasn't quite ideal. Okay, so let me quickly run over that. The left hand side here grows exponentially, so it's 2 to the power of 1 over c raised to the power of k, so some positive number raised to the power of k. And this right hand side here looks like it's growing linearly, but it's actually growing a lot faster than linearly, so we can't actually say that this guy here will eventually be bigger than this right hand side and reach contradiction. We've got to do a little more work, and the way we're going to do that is by modifying our n slightly. Anyway, let me clear up the whiteboard and we'll continue. Okay, so we just tried n being the product of the first k primes, and we showed that that didn't really work unless we made some further assumptions about the prime number theorem, but I'm not going to be doing that in this video because we can actually solve it without the prime number theorem if we modify this n slightly. And the way I'm going to modify it is just by raising this guy here to the power of m, where m is some arbitrary positive integer which I'm free to choose. Now notice that both k and m are essentially positive integers, or positive integers, which I am free to choose, and that will come into play in just a second because now I've got 2 guys which I can play with, whereas before I only had k which I could kind of choose, whereas now I have 2 guys to play with, and that should make the problem theoretically easier. Okay, so I'm just going to write this thing here, get rid of the brackets and distribute the m's over each of these primes like so. And then going back to this thing here, tau of n, let's just use our fact from before. Each of these ei's now are just m. So each of these brackets are going to be m plus 1, so that means tau of n is going to be m plus 1 to the power of k. And then our right hand side, as before, is just going to be log of this thing here. So log of p1 to the m times so on all the way up to pk to the m raised to the power of c. Now let's bring this over here. So we've got m plus 1 to the k, and in fact I'll take the cth root on both sides straight away, is less than or equal to just the thing inside the brackets now, log of p1 to the m times p2 to the m times so on all the way up to pk to the m. But of course, just using log rules, this is the same as m times log of p1, whoopsie daisy, plus so on all the way up to log of pk. And like before, I can bound each of these log of pi's by log of pk. So this is less than or equal to mk times log of pk. Okay, so we have this inequality here, and we want to choose m and k in such a way that this guy doesn't hold, and then we'll have a contradiction and we'll be done. But as I said before, we now have 2 guys to work with, m and k, whereas previously when we just had n being the product of the first k primes, we only had k to work with, but now we have k and m. And the issue we had before was with this log pk. We didn't really know how to bound that in a nice enough way to help us solve this problem. So what we should do is, if we're going to fix one of these variables and manipulate the other, is we may as well fix k in such a way, because then all we're left with is essentially m's, this guy here is a linear m, and this guy here is m raised to some power. So polynomials which we know how to deal with and know how to work with. So if we fix this log pk in a way, we should be able to manipulate m and choose an m in such a way that this inequality no longer holds. But what are we going to fix k to be? Well, it doesn't actually matter unless we, until we think about this guy here, this k over c. We want to show that for some m and k, this left-hand side grows bigger than this right-hand side. And if you think about it, if our aim is, or if what we're about to do is to fix k, then this guy here is just going to be some constant, k log pk, multiplied by m, so linear in m. and this left hand side here will be m to the power of k over c. So we want this left hand side to grow bigger than the right hand side, so we might as well choose k to be bigger than c, so that this guy here is bigger than 1. So this guy here grows bigger than linearly, so for sufficiently large m, this thing here will be bigger than that. Because we know polynomials, as you know, if you take x cubed and x squared, you know that for sufficiently large x cubed is going to be bigger than x squared, no matter what the coefficients are, or provided they're positive, I guess. But here we're only working with positive constants, so that's fine. Anyway, going back to this, we want to choose k being bigger than c, so let's do exactly that. We might as well just say let k equal to c, and because k has to be an integer, we'll just take the ceiling of that guy there. So then this left hand side here, m plus 1 to the k over c, is going to be bigger than or equal to m plus 1 to the 2c over c, sorry, which of course is just m plus 1 squared. And I guess we can say that this is bigger than or equal to m squared. So this left hand side here is bigger than or equal to m squared, but we know that, you know, if we just plug in now k equals 2c ceiling, so the ceiling of this guy here, fix k to be that guy there, we get that this right hand side now is just m times some constant, namely the ceiling of 2c multiplied by log of the ceiling of 2c prime, but it's simply a constant times m, so we get that m squared then must be bigger than, strictly bigger than, sorry, k log pkm, and that is for sufficiently large m. Because remember, this coefficient here is, you know, especially if c is big, this guy here is going to be really, really big. So we might have to choose m to be really, really big, but that's fine because that's allowed. So for sufficiently large m, we get this guy here. So for sufficiently large m. Okay, so we can just choose m to be really, really big. Okay, and then we see that this inequality does not hold. We do not get that this guy is less than or equal to that guy because we've shown that this guy here, i.e. this left hand side, is strictly bigger than the right hand side. Okay, and we arrive at a contradiction. I hope I wasn't waffling too much in that video, and I hope it all made sense. Essentially, it boiled down to being smart and choosing n in an appropriate way. The intuitive guess is to just do the product of the first k primes, but as we showed, that doesn't really take us anywhere nice. But then if we just raise everything to the m, we now have two variables we can work with, namely m and k, and then that allows us to solve the problem. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.